Okay, so in this video we're going to go through some reactions of alcohols, and um, this is more or less how the course works. There's like one more chapter where we do something called NMR, or nuclear magnetic resonance. But after that, it really does become just functional group reactions. How do you make them? What can you make from them? What are the mechanisms? So in that sense, the course becomes more predictable. Um, but it does usually get a lot harder for students because there are a lot of reactions. There are a lot of reaction mechanisms to learn. Um, the trick is, one, obviously don't fall behind in the course, but two is you have to really start looking for patterns. So that you don't end up having to memorize everything. And so these first reactions are a good example of that. I can take an alcohol and I can convert it to an alkyl halide. So this is sort of the reverse of the reaction that we looked at for making alcohols, where we took an alkyl halide and made it into an alcohol. Um, and we know about this reaction from our last section. This goes through SN1. I can do the same thing. So this is a tertiary alcohol. That's how I know it goes through SN1. If I have a primary alcohol, again, primary because it's attached to a primary carbon, and I subject that to HBr, now I can make the alkyl halide. But the mechanism has changed. It's now SN2. Okay, so we're just applying what we learned in the last section to avoid having to write out mechanisms again and again and again. This next one, this is secondary. Okay. And you might expect, when you subject this to HBr, for it to go through SN2. That's kind of what I would think, because Br minus is a good leaving group. Br minus is a good nucleophile. But what actually happens here is SN1. Okay. Why is it SN1? I don't know. We can make some arguments as far as why it goes that way, but people have studied it, and it looks like it goes SN1. So that's why. So you know, when we learn things in the last chapter, it makes it feel like there's always a clean, there's like this clean line for when something's going to go SN1 and SN2, and we can kind of make some predictions about that. But as you know from last chapter, secondary carbons have a tendency to kind of go and they have the potential at least to go through any kind of mechanism, and they're the least predictable. So it shouldn't be super surprising that you get these kind of weird cases where it goes SN1, and maybe you were expecting it to go SN2. Okay. So here is something. So these are all mechanisms that we know. You know how to draw those out. I'm not going to redraw those for you. If you're rough on those, go back and look through your notes or something. One thing that's interesting that can happen here is we can subject this to HBr. And the thing you'll notice here is this is a primary carbon, but off to the side here, we have a lot of what it's called beta branching. So this is our alpha carbon, and this is our beta carbon. Branching at the beta position indicates that we have to be concerned about rearrangement. The weird thing about this is, so you do end up seeing a rearrangement. So what you might expect would be just this if you had no rearrangement. The bromide would just swap out for hydroxyl group. This isn't actually what you see, though. Don't do this to me. There we go. This isn't what you see, though. What you actually see is this. Okay, so what's happened there is one of these methyl groups has just migrated over. This carbon is still this carbon. The green carbon is still the green carbon. So typically, we know, or you guys should know, that you have to watch out for carbocation rearrangements, or rearrangements in general, when you're forming a carbocation. The tricky thing about this, or sort of the weird thing about this, is that we know we're not going to form a carbocation here because you never, ever, ever form a primary carbocation. And so if we start looking at the mechanism here, this will hopefully make more sense that I draw out the mechanism. So we're in HBr. These electrons are going to come and get this. going to take the proton. Okay, now I've protonated my alcohol. It's a good leaving group. We're seeing rearrangement. Okay? Normally a rearrangement happens from a carbocation forming, so you might think this would happen, where you'd form a positive charge there, and then you would get, sorry, let me go and I'll draw in the methyl groups here to make it a little more obvious what the hell's going on. All right, so I've got a carbocation in the end, and you might think, okay, well this carbon here, make some indications so you can follow what's going on. We might get a shift there, a methyl shift. And there's nothing wrong, well, there is something wrong with this mechanism. But if you're thinking along these lines, you're doing pretty well. Like if you're following along and you're saying that makes sense, you're doing well. The problem with this, the overall problem with this, is just that this doesn't form. We never form primary carbocations. They're just so high in energy that they don't form. So that can't be what's going on there. Okay, so this mechanism that I've just drawn out it's not a bad thing to look over because it aligns well with what you already know, but it's wrong. And let's take a look at what actually goes on there. So this one's easier to follow, I think, than what I'm about to show you. So that doesn't happen. Oh, why is that? What am I doing here? That keeps reverting it back. There must be some shortcut on the Apple Pencil that I don't understand. Okay. Yeah, so what's happening there then if it's not that? So instead of the water coming off and forming a carbocation and then having the methyl shift, everything just happens at the same time. So the methyl shift comes over. Okay, so the electrons that are in, these things are just carbocation rearrangements in general are kind of weird. But the electrons that are in this bond they go with the CH3 group. Okay, and those electrons form a bond to the carbon that's attached to the leaving group, which is water. As that bond forms, another bond has to break, and that bond that breaks is the bond to the oxygen. And so we do sort of what we would have expected if we'd have formed the carbocation in a different step, but we just kind of do it all concomitantly. Okay, so now that's those electrons, that's that CH3 group, it's shifted over. This CH3 group is still here. Let's see what other colors I can get on there. This is that carbon atom, and our water is gone. Okay. So you'll notice now, go ahead and draw my hydrogens out. The thing that's changed here is this thing is now hypovalent. Okay, we're missing a bond there. If that's not clear to you, make sure you just kind of go through and track all of your bonds. The whole point of drawing mechanisms is to do bookkeeping on bonds that are forming and bonds that are breaking. So if you feel like you're not able to follow that and you're like, why is that positive charge there? Don't just kind of be like, I don't know, he drew it and keep drawing it. Go back and make sure that it makes sense what's happening with the electrons. That's the whole point of this. Okay, so now I've got this carbocation here, and I've got bromide floating around in solution, and that can come in. Ooh, I think I messed up my product in the first part. And attack there. So that's that. That's a CH3. Yeah, let's go back and look at what I did up here. So yeah, so my mistake was in my head, I put the bromine at the wrong carbon atom. Now I fixed that. Okay. So you can get rearrangements in, now that that's fixed, we can get rearrangements in alcohols. So you can get rearrangement specifically for primary alcohols. But the mechanism it involves simultaneous shifting of, in this case, a methyl group, but it could also be a hydride of the methyl and leaving group departure. And that's what we're showing here. So more important than kind of, jotting all that text down in your notes, although you're welcome to do that, that's what I'm trying to describe is what's happening in this step here. So make sure that you understand what's going on in that step. These electrons are they're attacking that orange carbon. The electrons that are in the purple bond are attacking the orange carbon. And the leaving group is departing simultaneously. Contrast this to what we've seen before for carbocation rearrangements, where the leaving group leaves, you form the carbocation, and then you have the rearrangement. Okay. Let's take a look at some other reactions. All right, so what if we want to avoid rearrangement? So let's say, most of organic chemistry, not for guys like me, I don't really do synthesis, but most of organic chemistry is around like being able to precisely build molecules. So if you get a rearrangement in one reaction, you'll want to have another reaction in your toolbox that allows you to avoid rearrangement. And that's what we're going to look at now. So let's say that you wanted to avoid rearrangement. So I've got this alcohol. I want to make a halogen there, right? Like I want to make this. We know from our last problem that if we add in HBr, we'll actually get is this. Okay, so that, so HBr will take us there. And we're wondering, like, well, is there a different way we can do this to where we actually get the Br where we want it? And the answer is yes. Chemists have developed a way to do this with PBr3. So we'll get a phosphorus in there. I think that's our first time seeing that in a reaction. Yeah, let's take a look then at what's going on here. So the mechanism for this is not super bad. The first step that's new to you is that the phosphorus, even though it has a lone pair on it, is actually an electrophile. So the electrons from the oxygen will go and attack there. You'll kick out the bromine, just like in an SN2 reaction. And now we have this species. So I'm going to draw your attention to this. In the last, normally what we're doing when we have a hydroxyl group is it's a bad leaving group. And so we'll protonate it. And that makes it a good leaving group. And so here we're kind of doing the same thing. Only instead of a proton, we have this group attached. So you notice it's charged just like H2O would be if it was attached. But now I've replaced one of the hydrogens with PBr2. I'm just drawing your attention to the kind of the patterns that are happening here. Okay, so now I've made what was a bad leaving group, this, into a good leaving group. We know this strategy. Even though the actors have changed, the story is still the same. Okay. There we go. All right, so what's going to happen now is this is going to come in and kick off that good leaving group. And now I have Br there. This last step should look familiar. This is just an SN2 reaction. So from here on in, it's SN2. Okay? So everything you know about SN2 reactions and stereochemistry and stuff all holds here for this reaction mechanism. But the nice thing about this reaction is you can do the halogenation. You can change an alcohol to a halide without having any kind of rearrangement. And this will work on primary and secondary alcohols. If you're wondering why it wouldn't work on a tertiary alcohol, think about it. If the last step is SN2, can it work on a tertiary alcohol? And the answer is no, right? We never see SN2 for tertiary carbons. Okay, let's look at this next one. So the more common reagent that you'll see if you work in a lab is, so what do we, no, I'm sorry, keeping with the theme of kind of making flashcards, here we have alcohol to alkyl halide. So unlike the last reactions where you're just doing like, in my mind at least, standard SN2, SN1 type stuff, where you shouldn't hopefully need to make flashcards. This one you want to make a flashcard for. How do I take an alcohol that's, you might want to note on your flashcard, primary, secondary, to an alkyl halide? You can add PBr3. We can do something similar. A more common reagent that you'll see is SOCl2 or thionyl chloride. Or if you want to use, I'll just put it up here at the top, you can also do SOBr2. In either case, you either substitute with the chloride or the bromide. So we did the bromide up there, so I'll do the chloride. SOCl2 is the more common of the two reagents. Okay, how does this mechanism work? Let's skip through kind of the first part. So the first part is similar to what you see, and we skip this mechanism as well, but it's the same kind of mechanism that you would see for tosylation. You'll notice that you have a sulfur, you've got the chlorine and stuff bound to it. We're just going to draw an arrow here without any arrows. Sorry, we're going to draw a normal reaction arrow without any mechanism arrows. And we're just going to skip ahead to the next part, which is this. And what we've done here again, even though this one's not charged or anything, is we've taken the alcohol, which is a crappy leaving group, and now, even though it may not be clear, it is a very good leaving group. Okay? Just like with the tosyl, when we tosylate something, we take the alcohol and make it into a good leaving group. The same thing is kind of happening here with thionyl chloride. This intermediate that I have here highlighted in orange, though, is really reactive. You wouldn't isolate this. What would happen is the Cl- that you kick off in the last step, so note that you've lost a Cl here. So I've got 2 on this side, and then when I come over here, I just have the 1. One of them got kicked off. Now that comes back in and does SN2. SN2. And now we've got our chloride there. Okay, so both of these strategies take us from an alcohol. Again, this will work with primary and secondary for the same reasons discussed above. You're doing SN2 chemistry, but these will work with an alcohol. It'll take it to an alkyl halide. Okay. So I'll go through briefly the implications of this being SN2. Actually, let's hold off on that. So I guess I'll say very, very quickly. We'll talk about this more when we go through synthesis. One of the interesting things about these reactions with PBr3 and SOCl2 is that if you do have stereochemistry, for example, like this, because you're doing an SN2 reaction, and you can look through the mechanism to make sure this makes sense to you, in the end, right, in the last step, what you're doing is an SN2 reaction. And what you end up getting out then is inversion of stereochemistry. And this isn't anything new per se. We know that you see inversion of stereochemistry for SN2. but the entire concept of SN2 is pretty new to us, so it's worth kind of pointing it out. So I'd get Br on there. And then if I wanted to take that through another reaction, and let's say I was doing another SN2 reaction on that, it would invert again, and you would get back sort of the original stereochemistry in the molecule. And the same is true for SOCl2. So when you use these reagents like PBr3 or SOCl2, just note that you will see an inversion of the stereochemistry, and it'll be a nice clean inversion. So if you're starting with something that's enantiomerically pure, as is the case here, just be aware that what you get out of it is going to be the opposite enantiomer. And when we work through the synthesis problems, maybe I can come up with something where we sort of use that to get the stereochemistry correct in the products. I try not to focus too much on stereochemistry because, at least in the reactions, because it's difficult. And obviously, when you're first learning synthesis and stuff, that in and of itself can be really difficult. Okay, this next reaction we're going to look at is, I'll write the name out, acid catalyzed dehydration of an alcohol. And I don't think I taught you about this. Sometimes I teach this earlier in the course, if it makes sense to do it. You'll notice here I'm saying dehydration, not hydration. So we've learned acid catalyzed hydration, which is if I take H2O and H2SO4, I will get an alcohol out. This reaction is actually reversible. I can dehydrate it and go back to the alkene. Okay, so how do I do that then? So this reaction is under equilibrium. And so I'm going to draw out like the other things that we don't typically draw out. So usually we're just worried about the substrate transformation. But really what we have here is water, and then we have H2SO4, but we have like a small amount of that. We're using like catalytic amounts of that, or let's actually, a word that maybe is more familiar with you, we'll just say dilute. So maybe you take a drop of H2SO4 and put it in there with water, and you get this out. The product is the alcohol. Obviously, you get a proton on there. How do we reverse it then? Oops, it's the same thing. If you want to reverse it, what you do is you put it under what's called dehydrating conditions. So now I take the alcohol and I use super concentrated H2SO4. And H2SO4 is dehydrating. It'll kind of pick up water. It kind of wants water, I guess. I don't know, that's a terrible scientific description. But H2SO4 kind of draws water into it. And so it'll force the equilibrium to go in the opposite direction. I guess a more informative way to think about it is like you'll form water at the end, and instead of thinking about the H2SO4, because I think that gets a little bit confusing, is imagine that you had a way to distill off the water. If this is under equilibrium, and we're thinking about this French guy who got his name attached to this, Le Chatelier. I don't know, my French isn't very good. But we've got this guy's principle. As we remove this product, we're going to force things to go to the product. Removing H2O forces equilibrium to the right. So Le Chatelier's principle is like a really, we learned about, you guys see that? I was looking at the GMAT because I was considering applying to business school at some point. I just miss being evaluated on exams. School has done that to me. Anyway, yeah. So Le Chatelier's principle. So yeah, we learned about Hammond's postulate and all this other kind of stuff, and that stuff can get a little bit heady at your level, but definitely Le Chatelier's principle you should get. So if we remove the product there, we can force the equilibrium to the right. And one way to kind of indicate that with the arrows would be to draw a really tiny arrow there. And a big arrow in that direction, right? So when we drew this before with this dilute thing, we kind of made it out like it was only going in one direction, but really it could go back in the opposite direction. If we put the right conditions down, we can force it to one direction or another. So, you know, on an exam, I don't know, if you were writing this for a synthesis, if we were actually in a normal class, where we weren't in a pandemic, we would probably accept H2SO4 by itself. You wouldn't have to indicate dilute or concentrated. I know some professors do require that. But pay attention to the concentration of it, I guess, to tell you which direction that reaction will kind of go. So one of the things you deal with in organic chemistry that you don't deal with on paper, and maybe you'll get this out of the lab. Sometimes I feel like people don't learn a whole lot in the labs. But yeah, one of the things you deal with are sort of these practical concerns, right? Like when you write something on paper like H2SO4 and we have all these things, we're not talking about concentrations, we're not talking about the conditions, how much you have to heat it, what the temperature is, how long the reaction has to go. Those are more practical considerations if you're actually trying to do a reaction. Let's see. Okay, I think that's good for reactions. So most of the reactions you already know. Our new reactions are PBr3 and SOCl2. In our next video, we'll go over oxidations of alcohols, which are super important. I'll give it its own video.